Great. So now we have a framework that allows us to talk about business cycle fluctuations that's consistent with long-term growth facts, and which also, as well as being able to enable us to talk about fluctuations in output, fluctuations in consumption, and fluctuations in investment, can now be used to talk about fluctuations in labor. However, the way labor is modeled so far is as a continuous variable, which is okay if we think of labor just in terms of hours worked. However, there are many macroeconomic aggregates about the labor market that are not in terms of hours. For example, the unemployment rate or the employment rate. There is no notion of unemployment in the models that we've seen so far. And in order to be able to say anything about those, we're going to need to adapt our models. Now, there are specific classes of models that have been developed precisely to talk about things like unemployment, such as search and matching models, in which there are frictions in the labor market, which mean that a person who wants a job can't necessarily find one immediately, and a job isn't necessarily immediately filled. However, it's going to be useful to extend our class of models in order to be able to talk about employment and non-employment, precisely because, as we started saying, this class of models is consistent with the growth facts, is useful for thinking about business cycles, and so on. So let's take a look. Now, one thing that might have bothered you so far is that we just put labor and leisure into our macroeconomy. However, one of the key macroeconomic variables that we're likely going to be interested in is unemployment. Of course, there is no notion of unemployment in this model. Or rather, more broadly, there's no notion of non-employment in this model. And we would like to find some way of doing that. Now, there are other classes of models, like search models, where there are labor market frictions that create unemployment, that may lead to unemployment. But it turns out that there's a way of creating a notion of unemployment, or again, non-employment, in the model we're looking at. So suppose the following is my utility function. I am maximizing, as before, the infinitely discounted sum of utility, and we'll say that this is leisure. However, let's say two things. First, agents leisure LT is from some set 0 to n. So n, big N, is our time endowment each period. Let's say that, as we were doing before, n is time spent working. So this can be rewritten such. Earlier we'd set this big N equals to 1. Doesn't really matter. You could always set it to any real number by just changing the units in which you measure your time endowment. And let's actually take a specific example. Let's say that this, as we saw before in the growth model, is the log of consumption plus some concave function of leisure, subject to consumption and investment being less than or equal to my labor income plus my capital income. And of course, with K0 given, and Z following some productivity process. I can write those assumptions out just for completeness. K0 given. Of course, we don't have that Z shows up here, so what I'm doing here is, as you can see, working with the market version of the stochastic problem we had last time. Of course, and the reason these are going to matter for the consumer, even in the market version of this problem, is because the wage and interest rate, those prices, are going to depend on the realization of this process Z. Now, this just looks the same as before. The new element I'm going to introduce here is suppose that there is a fixed work week or work time of length 1 each period. In other words, what we're doing is we're restricting the time spent working, N, to be either 0 if you're not working or 1 if you are working, and nothing in between. Now, of course, this means that in equilibrium, there will be some people working and some people who aren't working. Now, that's going to introduce a complication, of course, because everyone has the same utility function, but now based on your employment history, you may end up with agents who are not identical. You may actually want to do that. That may be something that you're interested in studying. However, it may not be. From a different perspective, you may be interested in having some notion of employment and non-employment, but not necessarily interested in the distributional consequences of that. You might be interested in just its implications for macroeconomic dynamics, which we'll return to soon, incidentally. So then, consider a way to preserve the representative framework, representative agent framework, even with this, what it's called is a non-convexity. Or you could also refer to this as indivisible labor. It's either 0 or 1. This is a non-convexity because this set here is not convex. There's 0, there's 1, and the values in between are not allowed. What's the solution to this? Is to introduce lotteries. So agents now choose a probability, call it H, of working. Now, when you studied game theory, you may remember that having mixed strategies, which of course introduces probabilities, is a way of convexifying things and ensuring things like existence. So you can think of it that way if you wish. Next, agents get paid HW regardless. In other words, the agent sells a state contingent contract to the firm where with probability H they work. There of course has to be a public randomization device, and they get paid HW regardless of whether or not they work. Notice that if N is total labor used in this economy, then with labor demand equals labor supply, if the number of agents we have is 1, as usual, this is a 0-1 continuum of agents, then total wage bill will be HW. And the total number of agents working will, of course, be H, if it turns out that everyone chooses the same probability H of working. So H will be employment, and 1 minus h will be non-employment. So let's just go with this. Let's see what happens on a particular date t. Let's suppress the subscript t for simplicity. If you work, you get log, in this period of course, C1, 1 corresponding to the fact that you're working, and then you get leisure of n minus 1, big N minus 1. If you don't work, you get C0, but you get more leisure. So your recursive problem becomes something like this. V of k and z equal to the max, and of course now choosing consumption, capital tomorrow, and h of, well, with probability h, you get this. With probability 1 minus h, you get this. And then we move on to the future. I'm just going to write expectation here rather than the whole integral for simplicity, since that's not what we're worried about now. Subject 2, what's your budget constraint going to look like now? Well, with probability h, you get C1. With probability 1 minus h, you get C0. And that's it. Now, remember that you're getting paid HW regardless. It's just that you find out at some point whether or not you get to work based on the realization of this randomization device that we're using. And what does that mean? Since everyone gets paid the same, it must be that C0 equals C1. And as a result, this problem is actually simpler. There is only one C, and what you get for sure, you're just randomizing over whether you work or not. Subject 2. This. There we go. Now let's rewrite some of this. I want to take this part, which is random here, and show you that it equals, this is just Vn minus h Vn. That's equal to, pull out the h, this, and if you define this, notice, to be a constant, because it is, this is just a number, and this is just a number, this becomes Vn minus some lambda h, where, of course, lambda is that constant. Lambda is, yes, the utility from leisure from not working minus the utility from leisure when you do work. And so if we plug that back in here, what do we end up with? We end up with this. And which is as though we were working with a representative agent who has a utility function that's linear in leisure. Or, put another way, that has linear disutility for working, h. And finally, this constant doesn't really do anything for us, right? It's not affecting agent's behavior in any way. If your utility were a particular function, your behavior would be the same as if your utility were that exact same function plus 6, or plus anything, or minus anything, any particular constant. So we drop it. And so now we're able to have a model with non-employment, even though we have a representative agent, by having two things. One was having a fixed work week, or rather more broadly, indivisible labor. And second, by introducing lotteries over who gets to work, and then of course those, also the wage contracts that are exchanged have to take those lotteries into account. But otherwise we're in the clear. Now I mentioned earlier that this was going to be something with macroeconomic consequences. It's useful that now we have notion of employment and unemployment. But there's another thing here. Consider the utility function for leisure, or the part of the utility function that concerns leisure that we started off with, which was v, little v. Here, this one. Now, of course, that's defined over the number of hours that these agents work. And on the other hand, this lambda, the marginal disutility of work, has nothing to do with v, really. It's just a number. It no longer has anything to do, to be precise, with the shape of v. So linear disutility of working is a very, let's call it, elastic function. It's going to give us very elastic labor supply numbers. Whereas the things that we usually think of as being utility functions are generally going to be strictly concave, not linear. If this is strictly concave, then it's probably going to give you a smaller elasticity of labor supply. Going to the data, when people were discussing these models, actually this discussion is ongoing, there was a discrepancy between microeconomic estimates of what the labor supply would be, which you might do by going around and seeing how a large number of people's hours varies when their wage changes, and using that to estimate V, compared to the elasticity of the aggregate labor supply, which seems to be much higher. The elasticity of labor supply at the micro level is closer to 0. The elasticity of macro labor supply appears closer to 1. And that was a puzzle. And of course, here is a perfectly good answer. What if labor is indivisible? If so, then the macroeconomic elasticity of labor supply doesn't depend much on what the microeconomic one is. The microeconomic one being the one that you might use to figure out what kind of function V should be. The macro level, if labor is indivisible, doesn't matter. All that matters is this difference. And then you end up with almost a linear utility function. And of course, then there's another empirical question, which is, over the business cycle, is it true that most of the variation in total hours has to do with people working more hours or fewer hours? Or does it have to do with more people dropping in and out of the labor market? What are these margins of dropping in and out of the labor market? Well, one of them is unemployment, but it's not the only one. One of them is retirement. One of them is going back to school, right? You might drop out of the labor market to take parental leave. And to the extent that things like that are important for variation in hours, then this picture here is more accurate than one where you assume that labor hours are continuous and that labor is not indivisible.